So we have seen how strong Lyapunov functions can be to give us information about the asymptotic stability of a critical point. Can we build it in practical cases? Let's look at an example. We have x dot equal 3x squared plus x sine of x, and y dot equals xy. 0, 0 is a critical point of the system, but linear stability analysis tells us absolutely nothing because linearly at 0, 0, this system is just 0. X dot equal to 0, y dot equal to 0. So going to linear approximations doesn't give us any information about what the system actually does. So let's try to build a Lyapunov function that tells us the stability of the critical point 0, 0. So let's try using xy squared. If we use xy squared, then the derivative of v with respect to the system turns out to be y second plus 3x squared plus x sine of x plus 2x squared y squared. Where x is small enough, that means we're close enough to our critical point 0, 0, then we can approximate sine of x by x. And we notice that v dot is positive definite because all the terms in v dot are a sum of squares. So that's great. We have found a Lyapunov function that gives us v dot that is positive definite. If we can prove that v is negative definite, we know that 0, 0 is a stable critical point. If we prove that v is not negative definite, then we know that 0, 0 is asymptotically unstable. Let's go for it. Well, we just check the sign of v for x and y possibly small, and v is x times y squared. Y squared has a positive sign, so v has the same sign of x. Then x is not positive definite and is not negative definite either. That means that v changes sign in any domain around the critical point 0, 0. That means that 0, 0 is asymptotically unstable. Notice how we haven't even checked the solution. We're already able to say that it is asymptotically unstable. Just to make things easier, there are some classes of functions that we can immediately say if they're positive definite or negative definite, such as this combination of squares, ax squared plus bxy plus cy squared is positive definite if and only if a is positive and 4ac minus b squared is positive. Notice that 4ac minus b squared being positive requires c being positive. The same function is negative definite if and only if a is negative and 4ac minus b squared is positive again. Because a is negative, in order for 4ac minus b squared to be positive, we need c to be negative. So you can flip a and c around and you notice that the sign keeps being the same. So this is an easy class to check being positive definite or negative definite. So if we can find a Lyapunov function of this shape, maybe we leave a, b, and c as unknowns and then we try to fix them afterwards. That will give us some information immediately about positive definiteness. Notice that if you're not fitting in the first section, positive definite, nor in the second section, it means that your function is changing sign around. That means that if that happens, if you're finding that your Lyapunov function is changing sign, then you immediately know that your critical point is asymptotically unstable. So let's try an example. We have x dot equals minus x to the third plus xy second, and y dot is minus x squared y minus y to the third. Again, linear stability analysis tells us absolutely anything, but we know that we have a critical point at 0, 0, and we try to figure out if this critical point can be stable or unstable. So I'm just gonna try out a Lyapunov function of the shape we just saw. So I'm just gonna guess v of x and y being equal to ax squared plus bxy plus cy squared. And I'm going to change A, B, and C in such a way that I can define V dot to be a specific sign, either positive definite or negative definite. So I'm going to compute V dot. It's a bit cumbersome, but it's just derivatives of polynomials. So we retrieve that V dot has a bunch of terms that are definitely positive, of which we know the sign. So we have minus 2a x to the fourth. X to the fourth is positive, so that block has a sign of a. And minus 2 times c minus a times x squared, that is positive, and y squared, that is positive. And then a block of things that have odd powers. So that block of things, we don't know if it has positive or negative signs, but it's all multiplied by b. So I'm going to choose b equal to 0, and I'm going to choose c to be bigger than a, bigger than 0. Because if I choose that, then the first term is minus 2a x4, that is always negative. The second term is minus 2 times c minus a, and c is bigger than a, times x squared y squared. So this second term is also always negative, and the other terms disappear because I choose b equal to 0. So if with this choice, I can find v dot being negative definite. Now with this choice, I want to check that v is either what I would like to find is that v is positive definite. If v is positive definite, I have proven asymptotic stability of my point. And v with our restriction is a sum of squares, a x squared plus c y squared. So v is positive definite, v dot is negative definite. Applying the Lyapunov theorem of stability, we have that 0, 0 is asymptotically stable.